Hello there, and welcome to the Sleepy Science Facts. Tonight, we drift gently into the ancient and extraordinary world of geology, the deep memory of our planet written in stone. Long before stars had names or oceans knew their boundaries, the Earth was already alive, quietly reshaping itself in silence. Mountains rose and slowly crumbled. Seas vanished, only to return again. Continents wandered across glowing oceans of molten rock. The ground beneath you is ancient beyond imagination, and yet it is still moving, still breathing, still changing. This is the story of geology, a story of fire and water, of creation and collapse, of beauty that takes millions of years to unfold. Beneath every step you take, within every pebble you see, there are whispers of volcanoes, glaciers, and stars long gone. If you enjoy these quiet journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. For now, just breathe. Let your eyes grow heavy. Let the ancient Earth cradle your thoughts. Let us begin. Earth's crust is thinner than you might imagine. If you could shrink the entire planet down to the size of an apple, the crust, the solid outer shell we live on, would be no thicker than the fruit's skin. The idea feels almost impossible, and yet it is true. The continents and ocean floors together form a layer that, on average, extends only about 30 kilometers beneath land and less than 10 beneath the sea. Beneath that lies the mantle, a vast region of slowly flowing rock that makes up most of Earth's volume and mass. The crust floats atop this mantle like fragile rafts, drifting on molten currents carried and reshaped by plate tectonics. Mountains, valleys, and ocean trenches are merely tiny ripples on the surface of an enormous sphere of stone. Everything we know, every forest, every city, every ocean, exists atop a layer so thin it nearly disappears when viewed on a planetary scale. Granite once flowed like molten rivers deep underground. Long before it hardened into the rugged stone we see today, granite was alive with heat. Deep within the Earth's crust, molten magma gathered in hidden chambers, moving like slow rivers of fire. Over millions of years, it cooled and crystallized into the familiar speckled rock that now forms the hearts of mountains. Each grain of quartz and feldspar once shimmered in a molten glow before solidifying forever. When you run your fingers across granite, you are touching the cooled remains of that ancient flow, frozen in time. Many of the world's great landscapes, from Yosemite's cliffs to the Scottish Highlands, were shaped by granite rising and solidifying beneath the surface. It holds within it the patience of the planet itself, a reminder that what appears solid today was once liquid light, slowly transformed beneath unimaginable pressure into something enduring and eternal. Diamonds can form in a heartbeat when conditions are right. Most diamonds take billions of years to grow deep within the mantle, born from carbon crushed and heated beyond imagination. But nature can be unpredictable. Under the most extreme pressures, carbon can rearrange itself into diamond almost instantly. These sudden transformations occur miles beneath the surface, where temperatures burn hotter than molten metal and pressures exceed anything humans can replicate for long. When volcanic eruptions bring these gems upward, they travel through narrow pipes of rock called kimberlites. carrying a story from the depths of Earth's creation. Each diamond you see, no matter how small, once existed in darkness and heat so fierce it could melt steel. Whether formed slowly or in a geological heartbeat, each crystal captures a moment when ordinary carbon became extraordinary. Born from chaos and pressure, rising toward light through the very bones of the planet, diamonds are nature's perfect record of transformation. Some mountains are still rising faster than your fingernails grow. Mountains may appear eternal, but they are alive with movement. Deep beneath the surface, tectonic plates push and collide, forcing rock upward inch by inch. In the Himalayas and parts of the Andes, this slow collision continues to lift peaks faster than your fingernails grow. What feels solid is actually part of an endless cycle of uplift and erosion. Wind, water, and ice tear mountains down grain by grain, while forces deep below rebuild them in a rhythm that is played out for hundreds of millions of years. A mountain may seem motionless, but if you could speed up time, you would see it breathe, swelling upward as continents collide. The stone beneath your feet may once have rested on the ocean floor, carried skyward over vast epochs. These giants remind us that Earth is not still at all, but in constant motion, reshaping itself even as we sleep. Entire continents float like rafts on molten rock. The ground beneath us drifts on a hidden sea of heat and stone. Beneath the crust lies the mantle, a region so hot that solid rock behaves like an incredibly slow-moving liquid. The continents rest upon this mantle as enormous rafts of rigid stone, drifting across it through deep time. They slide, collide, and separate at rates of only a few centimeters per year. Yet over millions of years, these tiny movements reshape the world entirely. Oceans open and close, mountain ranges rise, and entire climates transform. The continents we know are travelers, always in motion, though the journey remains invisible to us. This slow drifting once united all land into the supercontinent Pangaea, and one day it will bring the continents together again. Our planet is alive beneath its calm surface, and we are passengers upon its vast drifting plates, carried across geological seas without ever feeling the motion. Earth's surface is constantly recycling itself through plate tectonics. Nothing on the planet's surface is permanent. The continents and seafloors we see today are part of an endless process of destruction and renewal. Where plates collide, mountains rise. Where they separate, new ocean crust forms as molten rock wells upward. In other places, one plate dives beneath another and sinks back into the mantle, melting and becoming part of the Earth once more. Even the ground beneath the oceans is born, spreads, and disappears on a timescale of tens of millions of years. Every grain of sand, every cliff, every volcanic plain is part of this great planetary cycle. Earth is the only world we know that recycles itself so completely, using the slow power of heat and gravity to keep its surface young. The planet's skin is never truly still, but forever shedding and remaking itself in quiet, graceful motion. The Himalayas are still growing taller every single year. High above the clouds, these mountains continue their steady rise. Their growth began around 50 million years ago, when the Indian plate collided with the Eurasian plate, crumpling the crust like folded fabric. That collision is still happening, pushing the mountains upward by a few millimeters each year. The peaks may appear timeless, but their summits climb steadily toward the sky, even as wind and glaciers carve them down. Every tremor in the region, every deep earthquake, is a whisper of that immense pressure still at work. These mountains are not relics of the past, but the living result of an ongoing collision that began long before humans existed. The same forces that built Everest continue to reshape the land beneath millions of people. In their silent rise, the Himalayas remind us that Earth's power is patient, relentless, and always in motion. Continents drift as fast as your hair grows. If you were to measure the movement of a continent, it would advance about as quickly as your hair lengthens in a month. Yet over geological time, that gentle pace reshapes the entire face of the planet. Continents slide atop the mantle, carried by convection currents deep within Earth. The Atlantic Ocean grows a little wider each year, while the Pacific slowly shrinks. In millions of years, familiar maps will be unrecognizable. Africa will move closer to Europe. Australia will edge north. The continents may one day merge again into a single vast landmass. This slow drift connects fossils of ancient creatures found oceans apart and explains why mountain ranges on separate continents share the same origins. The ground feels solid beneath your feet, but it is part of a grand, restless voyage that has never stopped since the planet was born. The ocean floor is younger than most of the continents. Beneath the waves lies a hidden world in constant renewal. While the continents hold rocks billions of years old, the seafloor is surprisingly young. Along mid-ocean ridges, molten rock rises, cools, and forms new crust that slowly spreads outward. As it drifts, it eventually sinks back into the mantle at deep ocean trenches, where one plate slides beneath another. This recycling means no ocean crust lasts longer than about 200 million years, a fleeting moment in Earth's long history. The continents, by contrast, are ancient survivors that have floated above this cycle of destruction. If you could watch the planet's surface through time, you would see the oceans form and vanish like the rhythm of a breath. The seafloor is the planet's heartbeat, renewing itself endlessly, a reminder that even the deepest, darkest places on Earth are alive with motion and change. Magnetic stripes on the seafloor record Earth's ancient flips. Across the vast plains of the ocean floor, rocks are patterned like a barcode. These alternating magnetic stripes mark moments when Earth's magnetic field reversed direction, with north and south swapping places. As new crust forms along mid-ocean ridges, minerals within the lava align with the planet's magnetic field before cooling and locking that direction in place. Millions of years later, another reversal leaves the next band pointing the opposite way. By reading these stripes, scientists can trace a detailed history of magnetic flips stretching back tens of millions of years. This discovery was one of the keys that confirmed the theory of plate tectonics, revealing how the seafloor spreads outward over time. Beneath the oceans lies not chaos, but a perfectly ordered record of invisible forces, written in stone by magnetism, heat, and the slow pulse of geological time. Rocks can actually become magnets after cooling from lava. When molten rock cools on Earth's surface, something remarkable happens. Tiny particles of iron and nickel inside the rock align themselves with the planet's magnetic field, like invisible compass needles. Once the lava cools and hardens, those magnetic directions are locked in forever, preserving a snapshot of the field's orientation at that moment in time. Scientists study these natural magnets to map the shifting history of Earth's poles. Every reversal, every wandering movement of magnetic north is captured in stone. These magnetic fingerprints helped prove that continents drift and that seafloors spread. In every volcanic rock lies a silent record of Earth's magnetic pulse, whispering clues about ancient directions and the unseen forces that shape the space around our world. The planet's memory is magnetic, written in the iron heart of stone. Every volcano on Earth connects to a hidden magma chamber. Far below the surface, each volcano has a heart that beats with molten fire. These underground chambers are vast reservoirs of liquid rock, feeding eruptions that can reshape landscapes and alter climates. Some chambers are small and shallow. Others are immense and deep, reaching far beneath the crust. Inside them, crystals grow. Gases rise, and pressure builds until the rock above can no longer contain it. Then, with staggering power, the chamber releases its force through cracks and vents, pouring lava and ash across the world above. Between eruptions, these reservoirs remain hidden, slowly refilling and evolving. Modern technology allows scientists to glimpse their shapes using seismic waves, like ultrasound for the Earth. Each volcano is part of this deep, breathing network, a reminder that beneath calm fields and sleeping mountains lie vast, glowing worlds of molten stone, waiting quietly below. Some volcanic eruptions last for hundreds of thousands of years. Not all eruptions are sudden or explosive. Some are patient and relentless, flowing for ages beyond imagination. When mantle plumes release massive volumes of magma, the result can be a flood basalt, a vast outpouring of lava that continues for hundreds of thousands of years. These eruptions can bury entire regions beneath miles of solid rock. The Deccan traps in India and the Siberian traps in Russia stand as enormous relics of such ancient fire. During their reign, they released enough gas and heat to alter the planet's climate and change the course of life itself. Standing on these hardened lava plains today, it is difficult to imagine the molten rivers that once stretched to every horizon. They remind us that sometimes Earth reshapes itself not with explosions, but with the slow, unstoppable rhythm of fire spreading endlessly beneath the open sky. Basalt covers most of the ocean floor in dark, dense layers. If you could walk across the bottom of the sea, every step would land on basalt, a heavy, dark rock born of fire. It forms when molten material from the mantle erupts along mid-ocean ridges and cools rapidly upon contact with seawater. The result is a vast, unbroken crust stretching across the ocean basins like the planet's armor. Unlike the lighter rocks of the continents, basalt is rich in iron and magnesium, giving it both its deep color and weight. These solid layers are constantly renewed as the seafloor spreads outward, while older sections sink back into the mantle and melt once again. Every square inch of the ocean floor has been part of this endless cycle of creation and destruction. Beneath the waves, basalt holds the history of Earth's most patient movements, layer upon layer of cooled magma forming the quiet foundation of the world's oceans. Pillow lava freezes into shapes that resemble underwater balloons. When lava erupts beneath the ocean, it cools so rapidly that its outer surface hardens instantly, while molten rock continues to push outward from within. This process creates rounded, bulbous forms that look like pillows stacked upon one another. These formations, known as pillow lava, can cover entire stretches of the seafloor. Each pillow is a snapshot of fiery motion frozen in an instant, revealing how molten rock interacts with cold seawater. When geologists discover pillow lava on land, it tells them that the region was once deep underwater. The sight is both eerie and beautiful, as if the stone itself remembers flowing like liquid before being sealed by the chill of the sea. These shapes are geological sculptures of time, proof that even in the crushing depths, the planet's creative forces remain alive and active. Obsidian is volcanic glass cooled in an instant. During explosive eruptions, lava can cool so quickly that crystals never have time to form at all. The result is obsidian, a natural glass that gleams with dark, mirror-like beauty. Smooth, sharp, and reflective, obsidian forms when molten rock meets cold air or water and solidifies almost instantly. For thousands of years, humans have prized it for its razor-sharp edges, crafting blades, tools, and ornaments. Yet behind its polished surface lies a story of extreme change. Molten fire arrested mid-motion. Obsidian fractures easily, but along those breaks appear graceful, curved patterns known as conchoidal fractures, as if each break remembers the flow of the original lava. This dark stone stands as one of geology's most striking contrasts, born in violence, yet perfectly still, fragile, yet ageless. A piece of fire captured forever in the silence of stone. Some rocks preserve bubbles of Earth's ancient atmosphere. Trapped within the tiniest hollows of stone, scientists have discovered microscopic bubbles of air that have survived for millions of years. These preserved pockets act as time capsules, sealing the chemical signature of ancient atmospheres. By studying them, researchers learn what gases once filled the skies, how much oxygen existed, how much carbon dioxide warmed the planet, and how volcanic activity or early life altered the balance. Some of these bubbles formed in cooling lava, others within sediments or ice. Each contains an echo of an ancient breath, a ghost of the air that once surrounded early forests, giant reptiles, or the first life to breathe. To hold such a rock is to hold a fragment of vanished sky, a delicate record of the ever-changing air that connects all living things across Earth's long history. There are mountains higher than Everest hidden beneath the sea. Far below the ocean's surface lie vast mountain ranges that dwarf the world's tallest peaks. Along mid-ocean ridges, immense chains of volcanic mountains stretch for tens of thousands of miles, rising higher from their base to crest than Everest does above sea level. These submarine ranges remain mostly unseen, shrouded in darkness and immense pressure. yet they are among the most active regions on Earth. Lava continually emerges from fissures, building new peaks and valleys in slow, steady motion. Some of these hidden giants, such as Mauna Kea, surpass even the Himalayan summits when measured from their base on the sea floor. They remind us that much of Earth's grandeur lies unseen beneath the waves. Vast, silent kingdoms of rock that grow and shift in darkness, shaping the world from below without ever seeing the sun. Earth's deepest point is nearly as far below sea level as planes fly above it. At the heart of the Pacific Ocean lies the Mariana Trench, a chasm so deep that if Mount Everest were dropped into it, the peak would still be submerged by more than a mile of water. The trench's deepest known point, Challenger Deep, reaches nearly 11 kilometers beneath the surface, almost the same distance that passenger planes travel above the Earth. Down there, pressure is immense, crushing enough to flatten steel. Yet even in that darkness, life endures. Strange organisms glow in the black water, thriving among mineral-rich sediments. The trench marks a subduction zone where one tectonic plate slips beneath another and sinks back into the mantle. It is not only the lowest point on Earth, but one of the planet's great engines of renewal, a reminder of how small the visible world is compared to the vastness hidden below. The planet hums with micro-earthquakes you never feel. Even when the ground seems utterly still, it vibrates with the faint murmurs of constant motion. Across the planet, thousands of tiny quakes ripple through the crust each day, too subtle for humans to detect. These micro-earthquakes release small bursts of energy as Earth adjusts to stresses deep below. Scientists use sensitive instruments to record these whispers, mapping shifting faults and hidden magma flows. Together, they form a background hum that never ceases, the quiet pulse of a living planet. This ceaseless trembling reveals where faults are creeping, where pressure is building, and where volcanic systems are stirring. The stillness of the world is an illusion. Beneath every mountain, forest, and sea, the planet moves in countless subtle ways, sighing, cracking, and settling in slow, secret rhythms that carry the story of Earth's restless heart. Earthquakes can make entire rivers run backward. When the ground shakes with enough force, the landscape itself can change direction. During powerful earthquakes, the land can tilt or shift so abruptly that rivers are forced to reverse their flow. This rare phenomenon has been recorded during events such as the Great New Madrid earthquakes of the early 19th century, when sections of the Mississippi River temporarily flowed upstream. Sudden movement along faults can lift one side of the land or drop another, creating natural dams or lowering valleys in moments. For a brief time, the planet's internal forces overpower gravity itself. When balance returns, rivers carve new paths through altered terrain. These moments reveal the immense strength of geological motion, showing that even something as ancient and dependable as a river can be turned backward by forces hidden deep within the Earth. Some faults creep silently without any shaking at all. Not all tectonic motion announces itself with destruction. Along certain fault zones, The crust slides so slowly and evenly that there is no noticeable shaking at the surface. This quiet movement, known as fault creep, relieves pressure in small, continuous increments. It is invisible to anyone standing above, yet measurable with instruments sensitive enough to detect movement of only a few millimeters per year. Some faults in California and Turkey move this way, gliding smoothly while neighboring sections remain locked and tense. These creeping zones may reduce the likelihood of major earthquakes in some regions, but they also transfer stress elsewhere. This subtle balance between tension and release is part of the planet's constant adjustment. Even without noise or drama, the ground beneath us is always shifting, whispering in slow motion as Earth reshapes itself grain by grain across deep time. Earth's core is hotter than the surface of the Sun. At the very center of the planet lies a sphere of solid and molten metal under pressures beyond comprehension. Temperatures there exceed 9,000 degrees Fahrenheit, rivaling and even surpassing the visible surface of the Sun. This immense heat is leftover energy from Earth's violent formation, combined with the steady decay of radioactive elements deep inside. Though we will never see the core directly, it drives everything from volcanic eruptions to the magnetic field that shields life from cosmic radiation. The core churns like a vast dynamo, generating invisible lines of force that stretch far into space. The solid inner core rotates slightly faster than the planet above it, while the surrounding outer core flows as liquid metal. This hidden furnace is the beating heart of Earth, the power source that keeps our world alive with motion, warmth, and quiet resilience. There may be an entire ocean hidden deep within the mantle. Far beneath the crust, where rock glows with heat and pressure, scientists have discovered minerals that contain enormous amounts of trapped water. These findings suggest that a volume of water equal to several oceans may exist hundreds of miles below the surface, bound within crystal structures rather than flowing freely. It is not an ocean in the familiar sense, but a vast, hidden reservoir of the same substance that sustains all life. Tectonic plates may carry water downward into this deep realm, only for it to return through volcanic eruptions and rising plumes of molten rock. This unseen cycle could help explain why Earth has oceans at all. Even within the deepest stone, water endures, waiting patiently inside the mantle for eons. Crystals can grow larger than a person inside underground caves. Beneath the deserts of northern Mexico lies a cathedral of crystal, hidden deep within a silver mine. The Cave of the Crystals contains translucent gypsum blades stretching more than 9 meters long. Each crystal took hundreds of thousands of years to grow in perfect stillness, nourished by hot, mineral-rich water that once filled the chamber. When the water finally drained away, the crystals remained, gleaming like frozen moonlight in the humid air. Entering the cave feels like stepping into another world, one shaped not by violence, but by patience. The conditions required to create such formations are extraordinarily rare, balanced delicately between heat, saturation, and time. These massive crystals remind us that even the hardest materials on Earth can grow and change when given enough stillness. Giant gypsum crystals shimmer in Mexico's Cave of the Crystals. Discovered in the year 2000, this hidden chamber lies in an environment so hot and humid that equipment can fail within minutes. Inside, Towering beams of translucent stone stretch across the cavern, some weighing dozens of tons. They formed as groundwater remained at a stable temperature for immense spans of time, allowing molecules to arrange themselves with near-perfect symmetry. Once the cave was drained, the growth ceased, freezing the scene forever. Though no one can remain inside for long, brief visits reveal a vision of geological art created solely by time, water, and chemistry. Salt domes can pierce through rock like slow-motion explosions. In regions where thick layers of ancient salt lie buried beneath heavier rock, pressure can force the salt upward over millions of years. Though solid, salt behaves like a viscous fluid under stress. It rises through the rock above, bending and breaking it, forming dome-shaped structures that can reach miles in height. These domes often trap oil and gas, shaping landscapes and entire industries. From above, they appear as gentle swells. Below the surface, they are towering pillars of slow movement, reminders that even solid ground can flow given enough time. Each salt dome tells the story of ancient seas that evaporated long ago, leaving minerals that continue to climb skyward in silence. Petrified wood is quartz, atom by atom. What looks like a fallen tree turned to stone is something far more delicate. When a tree is buried beneath volcanic ash or sediment, mineral-rich groundwater slowly seeps into its cells. Over thousands of years, each microscopic structure of the wood is replaced molecule by molecule with quartz. Every ring, knot, and fiber is preserved in astonishing detail. The result is a fossil that still resembles wood, yet feels cold and heavy in the hand. Trace elements often tinted with reds, yellows, or greens, painting natural artwork within its grain. Holding a piece of petrified wood is like holding a memory made solid, a living thing transformed into crystal by time. It is nature's reminder that nothing truly disappears, it only changes form. Coal began as ancient forests trapped in swampy worlds. Long before humans walked the earth, vast tropical forests covered much of the land. When these forests died, their remains sank into oxygen-poor swamps where decay slowed almost to a halt. Layer upon layer of plant matter accumulated, compressed beneath its own weight. Over millions of years, heat and pressure transformed this buried organic material into coal, a dense rock made of concentrated carbon. Within every piece lies sunlight captured by prehistoric plants beneath an ancient sky. When coal burns, that sunlight is released once more, energy stored for eons returning in a ghostly glow. Oil comes from the buried remains of ancient plankton. Long before dinosaurs roamed the land, the oceans teemed with microscopic life. When these organisms died, they settled onto the seafloor, mixing with mud to form thick layers of organic sediment. As more material accumulated above, heat and pressure slowly transformed their carbon-rich remains into liquid hydrocarbons. Trapped within porous rock, these ancient molecules became the oil that fuels modern civilization. Every drop once drifted through a primordial sea, gathering sunlight through the simplest forms of life. The story of oil is one of geology, biology, chemistry, and deep time, woven together in darkness beneath the surface. Every grain of sand tells the story of a vanished mountain. Each tiny grain once belonged to something far greater, a towering peak, or ancient bedrock plain. Over millions of years, wind, water, and ice ground those rocks down into their smallest pieces. A single grain may have tumbled through glaciers, rushed down rivers, or drifted across oceans before coming to rest. Under a microscope, its shape and composition revealed the journey it took and the rock it came from. Every handful of sand is a library of broken worlds, fragments of mountains reduced to glittering dust that will one day be pressed back into stone. Desert sand can sing with a low musical voice. In a few rare deserts, shifting dunes produce deep, resonant hums that can last for minutes. These singing dunes, found in places like Morocco, Chile, and the Arabian Peninsula, generate tones so pure they seem to rise from the earth itself. The sound emerges as countless grains slide and collide in unison, vibrating at precise frequencies. Travelers describe the experience as haunting, as if the dunes are breathing or speaking. What sounds mystical is actually physics and friction, turning entire landscapes into instruments that play the slow, patient music of the planet. Some beaches are made entirely of tiny shells. Along certain coastlines, the sand beneath your feet was not carved from stone, but built by life. Over centuries, the shells of countless marine creatures broke down into fragments so fine they resemble powdered ivory. These biological sands can gleam white under the sun, glow pink from crushed coral, or shimmer gold from microscopic algae. Each grain is a fragment of something that once lived, a piece of the ocean's past returned to shore. Walking along such a beach feels like stepping through the ruins of invisible kingdoms, shaped by waves and time. There are black, green, pink, and even red sands on Earth. Not all beaches shimmer white or gold. Some are black from cooled lava, others green from olivine crystals, pink from coral fragments, or red from iron-rich volcanic rock. Each color tells a geological story about its source. Black sands form where lava meets the sea and shatters into glassy fragments. Green beaches appear where deep mantle minerals wash ashore. Pink sands come from crushed shells and coral, while red sands owe their hue to oxidized iron. Every shoreline is a palette painted by fire, water, and time. Glaciers carve landscapes like slow-moving rivers of rock. Though they appear still, glaciers flow. Over centuries, the weight of accumulated snow compresses into ice that slides downhill, reshaping everything in its path. These frozen rivers grind valleys, polish stone, and transport boulders for miles. When they retreat, they leave behind wide U-shaped valleys, scattered rocks, and shimmering lakes. From Yosemite's granite domes to Norway's fjords, glaciers have sculpted continents with quiet persistence. Some glaciers move fast enough to be seen. While most creep inches per day, a few surge forward so quickly their movement can be observed within hours. Meltwater lubricates their base, allowing massive sheets of ice to slide rapidly over rock. These sudden advances crack and groan as ice behaves like liquid stone. The sight compresses thousands of years of motion into a single moment, revealing the power hidden within frozen landscapes. Ice under pressure behaves like slow-flowing honey. Beneath the surface of a glacier, where pressure is immense and temperatures hover just below freezing, ice stops behaving like a rigid solid. Instead, it flows, slowly and continuously, folding and bending like honey poured in extreme slow motion. The crystals within the ice deform and slide past one another, allowing entire masses to creep downhill. This behavior gives glaciers their fluid grace and their power to carve mountains and shape valleys over tens of thousands of years. Under the right conditions, even solid rock behaves this way over geological time. What seems unyielding becomes supple with enough weight and patience. The planet's greatest transformations often occur not in sudden bursts, but through the quiet persistence of matter learning to move. Fossils can capture raindrops that fell hundreds of millions of years ago. Sometimes the smallest moments of the past survive in stone. On slabs of ancient sedimentary rock, scientists have found delicate impressions left by raindrops that fell onto soft mud long before humans existed. Each tiny crater records a single instant, a storm passing over a primeval landscape filled with strange plants and early life. Almost immediately, the marks were buried by fresh sediment, sealing them in darkness until the rock hardened. When exposed again, they reveal the touch of weather from a vanished world. These fossilized raindrops remind us that even fleeting moments can last forever when preserved by chance. Some fossils preserve soft tissues, even colors and feathers. For centuries, fossils were thought to capture only bones and shells. Yet rare discoveries have revealed impressions of skin, muscle, and feathers, sometimes even preserving traces of pigment. Under exceptional conditions, mineral-rich water replaces delicate tissues before decay can erase them. The result is life turned to sculpture, a frozen moment that shows how ancient creatures moved, breathed, and shimmered in sunlight. To hold such a fossil is to bridge worlds, touching warmth and color from beings long gone. Stromatolites record the oldest known life on Earth. Long before animals or plants evolved, simple microbes built layered structures in shallow seas. These formations, called stromatolites, were created by bacterial mats that trapped sediment and grew slowly toward the light. Some are more than 3.5 billion years old, making them among the earliest evidence of life on the planet. Remarkably, stromatolites still grow today in a few remote places. They remind us that life began not with speed or complexity, but with patience. Earth once turned completely white during Snowball Earth. Around 700 million years ago, the planet nearly froze solid. Ice stretched from pole to equator, sealing the oceans beneath miles of frozen crust and reflecting sunlight back into space. For millions of years, Earth became a silent world of ice, gleaming beneath a dim sun. Yet life endured, hidden in pockets of liquid water beneath glaciers and near volcanic vents. Eventually, volcanic activity released enough carbon dioxide to trap heat again, triggering a dramatic global thaw. This melting may have helped spark an explosion of complex life. Snowball Earth stands as one of the most dramatic transformations in planetary history, a near death followed by rebirth written in ice and stone. Volcanoes may have ended that frozen age with a greenhouse burst. While the planet lay frozen, volcanoes continued erupting beneath the ice, releasing carbon dioxide that slowly accumulated in the atmosphere. Once melting began, dark rock absorbed sunlight, accelerating the warming. In a geological instant, Earth shifted from frozen white to steaming blue-green seas. Floods reshaped continents, erosion accelerated, and life found new opportunities to flourish. Oxygen in the air was first made by ancient microbial mats. The air we breathe today exists because of tiny organisms that lived billions of years ago. These microbes used sunlight to split water molecules, releasing oxygen as waste. At first, that oxygen reacted with iron in the oceans, forming vast rust-colored deposits. Only later did it accumulate in the atmosphere, transforming the planet and enabling complex life. Every breath we take is a gift from those ancient microbes. Iron formations mark the moment the planet began to breathe. Banded iron formations, found worldwide, are fossil records of Earth's first oxygen-rich moments. Each layer marks a step in the planet's awakening, a heartbeat in the long transition from a lifeless world to one filled with air, oceans, and life. There was once a time when the seas were purple. Before oxygen filled the atmosphere, Earth's oceans looked nothing like they do today. The water may have shimmered with shades of red and violet, colored by ancient microbes that used sulfur rather than oxygen to capture sunlight. These organisms thrived in chemically rich seas beneath an orange-tinted sky, producing pigments that stained the water with unfamiliar hues. As oxygen-producing bacteria spread, these purple oceans slowly faded into the blue we recognize today. This transition reshaped everything: the atmosphere, the chemistry of rocks, and the future of life itself. For a brief moment in deep time, Earth glowed in colors we can scarcely imagine. Entire mountain ranges have vanished without a trace. The continents we see today are only the latest version of Earth's ever-changing face. In deep time, immense mountain ranges rose and were worn away so completely that no visible trace remains. Wind, water, and gravity patiently erased even the tallest peaks, grain by grain. Sometimes the roots of these ancient mountains survive as crystalline rock, buried deep beneath newer layers, leaving subtle clues for geologists to uncover. Over hundreds of millions of years, erosion can flatten mountains as effortlessly as waves smooth a pebble. What seems eternal to us is only temporary sculpture in the ongoing art of geology. Continents have collided and split apart many times. Over billions of years, Earth's land masses have gathered and scattered like slow-moving puzzle pieces. Driven by heat from the mantle, the crust folded, fractured, and rearranged itself again and again. Each collision built mountains. Each separation opened new oceans. This repeating process, known as the supercontinent cycle, has occurred many times throughout Earth's history. Rocks buried deep during collisions were reborn through heat and pressure, while new crust formed during separations, carrying fragments of lost worlds. The scars of these ancient migrations are visible today in matching fossils and rock formations found on continents now separated by vast oceans. The land beneath our feet is not fixed, but part of a restless dance that has never ended. There have been at least 6 supercontinents before ours. Long before Pangaea, and even before Rodinia, Earth assembled and broke apart multiple vast landmasses. Each supercontinent had its own mountains, climates, and oceans, rising and falling through deep time. Names like Nuna, Columbia, Rodinia, Pannotia, and Gondwana mark these vanished worlds. Their fragments remain scattered across the planet. When they existed, life was often microscopic, yet their formation shaped ocean chemistry and atmospheric evolution. Each breakup and reunion altered climate patterns and redirected evolution itself. The continents we recognize today are survivors of this immense cycle, pieces of ancient giants that spanned the globe. To study them is to read Earth's autobiography, written across billions of years, where even the land itself is temporary. Pangaea was only the most recent supercontinent. About 250 million years ago, nearly all land gathered into one vast body surrounded by a global ocean. This colossal landmass stretched from pole to pole, linking regions now continents apart. Its interior was harsh and dry, far from the sea's moderating influence, while its coasts supported early reptiles and forests. Over time, heat built beneath the crust until fractures split the land apart. The Atlantic Ocean opened, and the continents began their long drift toward modern positions. Fossils of identical plants and animals found on distant shores stand as silent witnesses to that ancient unity. Pangaea's breakup shaped today's geography and climate, setting the stage for everything that followed. The next supercontinent may already be forming beneath the Pacific. Far below the waves, the slow motion of tectonic plates is quietly preparing the next great rearrangement of Earth's surface. Scientists predict that in 200 to 300 million years, the continents may once again converge into a new supercontinent. Some models suggest the Pacific Ocean will close as Asia and the Americas move toward one another, forming a future landmass sometimes called Amasia. Others imagine the Atlantic closing instead, drawing Europe and the Americas back together. Though the outcome remains uncertain, the process itself is inevitable. The same invisible forces that tore Pangaea apart are still at work, shifting continents inch by inch. To imagine the world that far ahead is to realize how temporary our maps truly are. Somewhere deep within the Earth, the earliest motions of the next supercontinent have already begun. Australia is drifting north toward Asia every year. Beneath the Australian continent, the tectonic plate carrying it glides steadily northward at a pace of a few centimeters annually. Over millions of years, this gentle motion adds up to thousands of kilometers. Eventually, Australia will collide with the islands of Southeast Asia, raising new mountains and reshaping coastlines. Satellites already track this drift with astonishing precision. Though imperceptible to us, this migration alters climates, ecosystems, and ocean currents. Coral reefs grow where land once stood, and deserts slowly shift toward the tropics. Australia's quiet journey north is one of the planet's most graceful migrations. Africa may one day split into two separate continents. Deep within East Africa, a massive rift stretches for thousands of kilometers, marking a place where the continent is slowly tearing apart. Volcanic activity, earthquakes, and thinning crust reveal that a new ocean may eventually form. In tens of millions of years, regions including Ethiopia, Kenya, and Tanzania could break away and drift eastward. Lakes filling the rift's deep scars offer early hints of the ocean that may someday flood in. Standing at the rift's edge is like witnessing the birth of a future continent. Iceland sits directly above a tear in Earth's crust. The island exists because it straddles the mid-Atlantic ridge, where two tectonic plates are pulling apart. Here, Molten rock rises through a long fracture in the crust, creating new land as it cools. Glaciers rest beside active volcanoes, and geysers, hot springs, and lava fields reveal the restless energy below. Every eruption reminds Iceland's residents that their homeland is still under construction. Few places on Earth allow scientists to observe plate tectonics so clearly at the surface. Iceland is a living laboratory of creation, a place where the planet quite literally grows before our eyes, balanced between frozen seas and molten stone. The Hawaiian Islands are a moving chain built by a stationary hotspot. In the middle of the Pacific, a plume of molten rock rises from deep within the mantle, piercing the crust to form volcanoes. As the Pacific plate drifts northwestward, each new eruption builds an island that slowly moves away from the hotspot. Over millions of years, this process created a chain of islands and undersea mountains stretching thousands of kilometers. Hawaii remains volcanically active, while older islands have eroded into low atolls. By tracing this chain, scientists map the movement of the Pacific plate through time. The hotspot stays fixed, while the surface glides above it, leaving a dotted trail of creation written in stone. Yellowstone is powered by a massive supervolcano beneath the surface. Beneath the calm forests and steaming geysers of Yellowstone National Park lies one of the largest volcanic systems on Earth. A vast reservoir of molten and semi-molten rock stretches deep beneath the surface, fed by a powerful mantle plume. This system has produced some of the most enormous eruptions in Earth's history. When it last erupted explosively, it reshaped landscapes across North America, covering entire regions in ash. Today, the volcano remains active, though its eruptions are mostly gentle. Geysers, hot springs, and subtle ground movements revealing the heat below. Though dramatic headlines often exaggerate its danger, Yellowstone is carefully monitored. It stands as a reminder of the immense forces that still sleep beneath seemingly peaceful ground. Supervolcano eruptions can alter the global climate. Unlike typical eruptions, supervolcanoes release thousands of cubic kilometers of material in a single event. Ash clouds can circle the globe, blocking sunlight and cooling the planet for years. Such eruptions may trigger volcanic winters, disrupt ecosystems, and influence the course of evolution. Evidence of past super-eruptions appears as thick ash layers found continents away from their source. These events are rare, but their impact is unmatched. Geological moments capable of reshaping life on Earth. Volcanic ash can travel around the entire planet. Fine particles ejected high into the atmosphere can remain suspended for years, drifting across oceans and continents. Eventually, this ash settles, enriching soils with minerals. Some of the world's most fertile farmland owes its richness to ancient volcanic eruptions. What once darkened skies and chilled climates later nourished forests and crops. Even destruction feeds creation in Earth's long story. Ash layers serve as time markers for scientists. Because volcanic eruptions spread ash over vast areas in a short time, these layers form precise timestamps in the geological record. By matching ash layers between distant regions, geologists align timelines and reconstruct past environments. A thin gray band in rock can represent a single violent moment frozen forever. These layers act like bookmarks in Earth's memory, allowing scientists to read the story of deep time with remarkable clarity. Volcanoes release more than lava and ash. Gases such as water vapor, carbon dioxide, sulfur dioxide, and hydrogen sulfide pour from vents during eruptions. These gases influence climate, air quality, and even ocean chemistry. In small amounts, volcanic gases help regulate Earth's long-term temperature. In large bursts, they can cool the planet or trigger acid rain. The invisible emissions are often more influential than the glowing lava itself. Some eruptions are heard across continents. The eruption of Krakatoa in 1883 was so powerful that it was heard thousands of kilometers away. Shock waves circled the globe multiple times, and the explosion altered sunsets worldwide. Though such eruptions are rare, they demonstrate how energy stored within the Earth can be released in moments of staggering force. The sound of a volcano can echo around the planet, a reminder of how tightly connected Earth's systems truly are. Meteorites fall to Earth more often than most people realize. Every single day, tons of cosmic material enter Earth's atmosphere. Most of it burns away as streaks of light, but some fragments survive the journey and land on the surface as meteorites. These space rocks are among the oldest materials humans can touch, formed over 4.5 billion years ago during the birth of the solar system. Some contain tiny grains that predate the sun itself. Holding a meteorite is like holding time older than Earth, a visitor from a distant chapter of cosmic history. Impact craters reveal violent moments frozen in stone. When large meteorites strike the planet, they release energy equivalent to millions of nuclear bombs. The ground vaporizes, rock melts, and shock waves ripple outward, leaving vast circular scars. Some craters are easily visible from space, while others have been softened by erosion or hidden beneath sediment. Beneath many forests and seas lie the remains of ancient impacts, silent reminders of moments when the sky fell and reshaped the land in seconds. The moon was likely formed by a colossal collision. Billions of years ago, a Mars-sized object may have slammed into the early Earth. The impact ejected vast amounts of molten material into orbit, which gradually coalesced into the moon. This theory explains the moon's composition and its unusually large size compared to Earth. The collision altered Earth's rotation, stabilized its tilt, and may have made life possible. Our closest celestial companion is the child of catastrophe, born from chaos, yet essential to the calm rhythms of tides and time. Moon rocks closely resemble Earth's mantle. Samples brought back by astronauts reveal striking similarities between lunar rock and Earth's interior. This shared chemistry supports the idea of a common origin following a massive impact. The moon carries the memory of Earth's early molten state, preserved on a surface largely unchanged for billions of years. While Earth's geology constantly renews itself, the moon remains a quiet archive of the solar system's violent youth. Large impacts have reshaped life on Earth. Throughout history, asteroid impacts have triggered dramatic changes. The most famous struck 66 million years ago, contributing to the extinction of the dinosaurs. Dust and debris blocked sunlight, disrupted food chains, and reshaped ecosystems. Yet from that destruction arose new opportunities. Mammals diversified, ecosystems transformed, and the modern world slowly emerged. Impacts remind us that evolution is shaped not only by gradual change, but by sudden cosmic interruptions. Tiny space dust rains down constantly, Even on calm, clear days, microscopic particles from space drift down through the atmosphere. These grains settle into oceans, soil, and ice, adding extraterrestrial material to the planet year after year. In polar ice, scientists can measure layers of cosmic dust and trace changes in Earth's passage through space. Our planet is not isolated. It is constantly exchanging material with the wider universe. The Moon is slowly drifting away from Earth. Each year, the Moon moves about 4 centimeters farther from our planet. This gradual retreat is caused by tidal interactions between Earth and its lunar companion. As tides rise and fall, energy is transferred from Earth's rotation to the Moon's orbit. Over time, this slows Earth's spin while pushing the Moon outward. Billions of years ago, the Moon appeared much larger in the sky, and days on Earth were significantly shorter. This gentle separation shapes the rhythm of our planet, influencing tides, climate stability, and even biological cycles. The Moon's quiet drift is a reminder that celestial relationships, like geological ones, evolve slowly but relentlessly. Days on Earth are getting longer. As Earth's rotation gradually slows, days lengthen by tiny fractions of a second each century. Though imperceptible in daily life, this change is precisely measured using atomic clocks and ancient eclipse records. Long ago, a day lasted only about 22 hours. In the distant future, Earth's day will stretch even longer. The slowing spin affects atmospheric circulation and ocean currents, subtly shaping the planet's climate over deep time. Tides once played a key role in the emergence of life. The rhythmic rise and fall of ancient seas created shallow pools that repeatedly dried and refilled. These cycles concentrated chemicals and encouraged complex reactions that may have led to the first living cells. Without the Moon's stabilizing influence, Earth's tides would be weaker and less regular. Life's earliest steps may have been guided by the gentle pull of a distant companion in the sky. Earth's tilt is stabilized by the Moon. The angle at which Earth leans as it orbits the Sun gives rise to seasons. Without the Moon, this tilt could wobble chaotically, causing extreme climate swings. The Moon's gravitational presence acts as an anchor, keeping Earth's axis relatively stable over millions of years. This stability allowed life to adapt gradually rather than face constant upheaval. In a quiet way, the Moon has been a guardian of habitability. In the distant future, solar radiation will reshape the planet. As the Sun ages, it will slowly grow brighter. Over hundreds of millions of years, increased radiation will heat Earth's surface, affecting oceans and atmosphere. Water may begin to evaporate more rapidly, and geological cycles could slow as plate tectonics weakens. Though this future lies far beyond human timescales, it is part of Earth's long story, a reminder that even planets evolve and age. One day, Earth's oceans may disappear. If solar heating continues unchecked, oceans could gradually boil away, leaving behind dry basins and salt plains. The world would resemble a hotter, quieter version of Venus. Yet long before that happens, life will adapt or migrate, and new forms may emerge. The planet's future, like its past, is a story of transformation rather than ending. Carbon moves endlessly between air, rock, water, and life. The carbon cycle is one of Earth's deepest and most powerful systems, quietly linking geology and biology. Carbon drifts through the atmosphere as gas, settles into oceans, becomes locked in stone, and returns again through fire and time. Volcanoes release carbon dioxide from deep within the mantle, returning ancient carbon to the air. Rain absorbs that gas, forming weak acids that slowly dissolve rock. Rivers carry dissolved carbon to the sea, where it becomes part of shells, skeletons, and seafloor sediments. Over millions of years, these sediments are buried, compressed, and transformed into limestone and other rocks. Eventually, tectonic forces carry them downward, melting them and completing the cycle. The breath of forests, the shells of oceans, and the fire of volcanoes are all expressions of the same circulating element. Rocks themselves can be said to breathe. Through chemical weathering, stone absorbs carbon dioxide from the air, locking it away in minerals. This slow process helps regulate Earth's climate, preventing runaway heating or cooling. Without this geological breathing, the planet might have become hostile to life long ago. The balance between volcanic release and rock absorption has kept Earth within a narrow, life-friendly range for billions of years. Stone records climate like a memory etched in layers. Sedimentary rocks preserve detailed histories of ancient environments. Each layer tells a story of temperature, rainfall, ocean chemistry, and life. Limestone reveals warm, shallow seas. Coal records humid forests. Evaporite layers mark ancient deserts where water vanished under intense sun. Together, these stones form a climate archive far older than ice cores or tree rings. Even tiny chemical signatures can reveal ancient temperatures. Ratios of oxygen isotopes in shells and minerals shift depending on climate. By reading these ratios, scientists reconstruct ice ages, greenhouse periods, and transitions between them. The Earth has swung between extremes many times. Ice once reached the equator. At other times, crocodiles swam near the poles. Life survived each transition, adapting to new rhythms shaped by rock, water, and air. Climate change is not new to Earth, but today it is unfolding faster than most past shifts. The rocks remind us that change is natural, yet pace matters. The planet adjusts slowly. Life depends on time. Deep time stretches far beyond human intuition. Geological time is measured not in years or centuries, but in millions and billions of years. In this vast scale, entire civilizations are brief flashes, while mountains rise and vanish like passing clouds. Rocks move through this deep time slowly, almost imperceptibly. A grain of sand may spend millions of years buried, transformed into stone, uplifted into a mountain, and ground back down again. Nothing is rushed. Everything unfolds with immense patience. Fossils, minerals, and tectonic scars allow us to read this deep past. They show that Earth has never been static. Continents drift, climates swing, oceans open and close, and life responds again and again. Deep time is the stage on which all of this plays out. To understand geology is to step outside ordinary time. It invites the mind to slow down, to release urgency, and to sense the planet's quiet endurance. In deep time, even catastrophe becomes part of continuity. Plate tectonics will not last forever. The movement of Earth's plates is driven by heat escaping from the planet's interior. As the core slowly cools over billions of years, this engine will weaken. When tectonics finally slows and stops, mountains will no longer rise. Volcanoes will fall silent. The recycling of crust will cease, and the surface will begin to smooth and settle. Erosion will continue, but renewal will fade. Without tectonics, the carbon cycle will weaken. Climate regulation will falter. The planet will become more stable, but also less dynamic. A quieter Earth, older and calmer, will emerge. This future lies unimaginably far ahead. Yet it reminds us that even the processes we consider eternal are temporary in the planet's long life. When the planet finally grows quiet, erosion will become the dominant force. Wind, rain, and temperature will slowly wear down what remains of mountains and plateaus. With no new uplift, the continents will gradually flatten into vast, low plains. Rivers will meander lazily across these ancient surfaces, carving gentle paths rather than deep valleys. Coastlines will smooth as cliffs crumble and sediments settle into shallow seas. The drama of collision and eruption will fade into a long, peaceful stillness. The sky may look much the same, but the earth beneath will be older, softer, and less restless. The planet will no longer build, it will only remember. Even in this quiet future, time will continue to flow. Minerals will still rearrange at the atomic level. Crystals will grow and dissolve. Heat will slowly leak into space. Life, if it remains, will adapt to the calmer rhythms of a cooling world. Simpler ecosystems may dominate, tuned to stability rather than change. The Earth will breathe more slowly, its pulse faint but steady. This stage of the planet's life is not an end, but a resting phase. A long twilight between transformation and silence. Against the immensity of geological time, humanity is a moment. All of recorded history fits within the blink of an eye compared to the age of a single mountain range. Cities rise and fall faster than rocks can crack. Yet humans, too, are part of geology. Our bones are made of calcium once carried by ancient seas. The iron in our blood was forged in stars and locked into the planet long before life began. Every breath connects us to volcanic gases and fossil sunlight. When we build, we reshape the surface. When we dig, we uncover memories written in stone. Even our ruins will one day become layers, pressed into future rock. In time, the traces of our presence will thin and fade, but they will not vanish completely. We are not separate from the planet. We are one of its brief expressions. As night settles, the Earth continues its slow work. Beneath sleeping cities and silent forests, pressure builds and eases. Heat moves quietly through stone. Water seeps through fractures, carrying minerals grain by grain. Nothing stops, it only slows. The planet does not hurry, and it does not forget. Every mountain remembers being sea. Every crystal remembers fire. Every grain of sand remembers a larger whole. To rest upon the earth is to be held by something unimaginably old and endlessly patient. The ground beneath you has carried continents, oceans, and skies, and it carries you now without effort. As you drift toward sleep, imagine the planet beneath you breathing in deep time. Imagine the slow turning of stone beneath stars that once forged the elements of your body. Let the thought of vast ages quiet your mind. Let the weight of mountains and the gentleness of sand settle your thoughts. You are safe within a world that has endured fire, ice, impact, and darkness, and still continues. The earth does not rush, and neither must you. Breathe slowly. Let your eyes grow heavy. Let the ancient planet cradle your thoughts, steady and eternal. Sleep well.